This is Chapter 12, Part 8. We're going to be discussing action potentials. So an action potential, or an impulse, this is a sequence of rapidly occurring events that decrease and reverse the membrane potential, and then eventually restore it back to its resting state. So an action potential has two main phases. We're going to have the depolarizing phase and then the repolarizing phase. So during the depolarizing phase, the negative membrane potential becomes less negative, it reaches zero, and then it becomes positive. During the repolarizing phase, the membrane potential is restored back to its resting state of negative 70 millivolts. An action potential occurs in the membrane of the axon of a neuron when depolarization reaches a certain level. So we're going to have depolarization of the axon all the way down to the axon terminals here. And this action potential occurs when the depolarization reaches this level called a threshold. And threshold is negative 55 millivolts in most neurons. So here you can see the stimulus that brings the membrane potential from negative 70 millivolts and it brings it up to negative 55 millivolts, which actually causes an action potential and initiates the depolarizing phase. Now, once the membrane reaches about positive 30 millivolts, this is when it starts the repolarizing phase. Following this phase, we have an after hyperpolarizing phase, and this is when the membrane potential temporarily becomes a little bit more negative than its resting potential. Here on the right side of this figure, we have this key. And this is a really great key to show what ion channels are open during each phase of the action potential. So during the regular resting membrane potential, we have this kind of a purpley color here at the beginning, and this is when all voltage-gated channels are closed. They're all in resting state, so none of the potassium or sodium ions are getting through. Keep in mind we do still have those leakage channels, so they're very small amounts of sodium and potassium that are going through, but the voltage-gated channels are all going to be closed. After we have this stimulus, it causes depolarization to threshold to that negative 55 millivolts. And once the cell reaches a threshold, we start this green part here. Once it reaches threshold, we have voltage-gated sodium channels that are activated, they open, and then we have a lot of sodium that just rushes into the cell, bringing the cell potential positive very, very quickly, as you can see here in this depolarizing phase. So because that sodium all rushes into the cell super quick, we have the inside of the cell comes positive very quickly from that sodium influx. And this is going to be the depolarizing phase. Now, after a certain time, the voltage-gated sodium channels deactivate. We're gonna talk about that a little bit later. And at this time, we also have the voltage-gated potassium channels open as well. So I'm going to have a quick little note here. At this point, when we reach threshold, all voltage-gated channels in the area are opened, but the voltage-gated sodium channels open much quicker than voltage-gated potassium channels. So voltage-gated sodium channels, they open and close very fast. Very fast. Whereas voltage gated potassium channels are slow. So at this point here, all of them open. The voltage gated sodium channels open very quickly, and the potassium channels open as well. At least they start open, but the potassium channels don't actually fully open until we hit this peak of the graph. In the repolarizing phase, this is when the potassium channels are open and the positive potassium ions start to leave the cell, and we're going to start bringing that voltage change between the inside and the outside of the cell back down, because those positive ions are going to be leaving the cell, bringing the cell back to a more negative state. Because the potassium channels are also very slow to close, they are open a little bit longer. And this allows more potassium ions to leave the cell than we kind of want. And this causes the cell membrane to go a bit more negative than resting potential until they all close completely, and then the cell is back to resting potential. So in this after hyperpolarizing phase, we have these voltage gated potassium channels are still open because they are just really slow, and they're still allowing that potassium to leave the cell, and it causes actually it to be a little bit more negative than the regular resting membrane potential. And that's when these sodium channels are in a resting state. Also, these refractory periods, you can make note of them now, but we will talk about them in a few slides. Okay, so the generation of an action potential depends on whether a stimulus is able to bring the membrane potential to threshold. So an action potential will not occur in response to a sub-threshold stimulus, a stimulus that's not strong enough to actually bring the cell to negative 55 millivolts. This is a very weak depolarization, and it can't bring the membrane to threshold. An action potential will occur in response to a threshold stimulus though. So this is a stimulus that's just strong enough to depolarize the membrane to threshold. So it's just strong enough to get it right up there to negative 55. And once we hit this threshold, that's when all those sodium channels open and sodium rushes into the cell, and we're going to bring that voltage or that membrane potential up to positive 30. Several action potentials will form in response to a suprathreshold stimulus. So the stimulus is really strong, and it's strong enough to depolarize the membrane above threshold. And so we're actually going to get several action potentials from one suprathreshold stimulus. So this figure here shows the steps of an action potential in regards to the ion channels. So as you can see in the pictures, the green colored voltage gated sodium channels are a little bit different from the other channels in that they have this activation gate in the center here that opens and closes, but they also have this inactivation plug as well. So they're a little bit different. Here the potassium channel just has this one gate at the bottom, but we're going to go over this and kind of learn what that inactivation gate actually does as well. So in step 1 here, this is going to be the resting state. As you can see, both the sodium and the voltage gated channels are closed. So we have the activation gate is closed on the sodium voltage gated channel, and the gate is also closed here on the potassium channel. This inactivation gate though on the sodium channel is open, but because this activation gate is closed, no ions are actually going through. Next, once there is a stimulus to the cell that brings the membrane to threshold potential, we reach that depolarizing phase. This is when you can see that the voltage gated channels open. And the sodium, as you can see here, these little green ions are going to rush into the cell, increasing the buildup of positive charge inside the membrane, and then the membrane becomes depolarized. So you can see on this graph here, we're going to increase the charge inside the cell. As soon as the sodium channels open, they start to inactivate. And this inactivation is completed once the cell reaches positive 30 millivolts. So this is when repolarizing phase begins, once we hit that positive 30 millivolts. And this is just an arbitrary number that we know neuron cells will reach to. So here you can see this inactivation plug is closed in the sodium voltage gated channels. They are still technically open though. As you can see, this activation gate is actually open. But even though they're still open, they are deactivated. Now at the same time that the voltage gated sodium channels are being inactivated, the voltage gated potassium channels are opened. So you can see here these channels are open and some potassium ions are going to be leaving the cell, these little triangular like yellow ions. And a few negative ions are going to be built up on the interior of the cell. Now throughout the repolarization phase, the potassium ions will continue to flow out of the cell, and eventually this will restore the resting membrane potential. During this phase, the sodium channels close completely. As you can see here, now they're completely closed and the inactivation plug is going to be removed. This happens during the repolarization phase. Once the potassium gates are all closed, then the resting state is returned to normal. So as soon as these potassium channels start to open in this phase, in the repolarizing phase, they actually start to close as well. So it takes them all this time from here all the way to here to open, and at this point they actually start closing. This is when they're actually completely open, and that's when they start closing. So they start closing and it actually kind of dips down until we get back to our resting membrane potential of -70. But it takes these potassium channels a long time to close. Looking back at this figure again, we're going to talk about the two figures that we didn't talk about earlier. These are the absolute refractory period and the relative refractory period. Now the absolute refractory period refers to the period of time during which another action potential cannot fire no matter how large the stimulation is. This absolute refractory period starts here when the sodium channels first open and ends about here. This absolute refractory period is mainly due to the voltage-gated sodium channels being inactive, remember with that inactivation plug in the bottom, and they are completely unable to reopen during that time. The relative refractory period, this is when another action potential can fire, but only if the stimulation is very large. This is the time when most of the sodium channels are still inactive and the potassium channels are still closing, so it is quite difficult to have another action potential. And that's going to be right here after that absolute refractory period to after hyperpolarizing phase. So this is when you need quite a large stimulus to have a second action potential fire during that time. So here we have a table that has a really good comparison between the graded and action potentials. So here it shows you the different places that we're going to find them, their origins, mainly the dendrites and cell body, and here we're only going to have on the axons. The conduction speeds or the conduction abilities, remember in the graded potential they're going to be decremental, so they're going to die out over a distance. So this is really a short distance type of communication, whereas action potentials we can communicate over longer distances. Again, amplitude is quite important, so we can depend on the strength of the stimulus is going to give us how large of a graded potential we're going to get. But action potentials, it's all or none. This is a really good phrase used in action potentials. It either happens or it doesn't. You either bring that cell up to its threshold to fire an action potential, but anything below threshold in action potential will not fire. And then we have these refractory periods. So there's no refractory period in graded potentials, but in action potentials we do have them. Also talks about summation as well. Remember we did talk about summation in graded potentials, but we actually can't have summation in action potentials, and that's because it's that all or none kind of phrasing again. Either it happens or it doesn't. You can't really summate different stimuli in order to make an action potential larger or smaller. It has one action potential, one amplitude that the action potential will reach. And that's going to be the end of Chapter 12, Part 8.